Hello again. Thank you for coming back and preparing to watch the second part of Chapter 5. And again, I'm reminding you that there is material in the course collateral that you can read along with this, as well as your book. And please feel free to use all those buttons associated with YouTube. We're going to move to considering a more realistic situation where things don't continue on forever. There are things like friction, air resistance, and in this case, water. So what we're really saying is pretend that we put the mass into a fluid like water. It's going up and down, but the fluids will retard the motion and will be opposite of the direction of the motion. So if you're pushing down, the fluid will be pushing you back up. If you're pushing up, you're pushing against the fluid as well. You could also think about this as being arranged with a piston, and this is much more realistic. Now, what we're going to assume right now is we're going to assume that the damping is proportional to the velocity, and that means it's proportional to dx dt. Now, what's going to happen in your take-home problem, there's going to be a different assumption I ask you to make, but that's the assumption that we're using right now. So when no other external forces are impressed on the system, from Newton's law, what happens is we have it as before, except now we have a force that's pushing back, and I'm using a coefficient of beta, where beta is a positive damping constant, and the negative sign is a consequent effect that the damping force acts in a direction opposite to the motion. So putting that into my differential equation, then get everything on the same side, dividing all the way through by the mass, we get that kind of a differential equation, and then just reorganizing this a little bit. For convenience, they tend to call beta over m 2 lambda, but we arrange this and we have this kind of differential equation, which according to operators is like this, and we know very well how to solve that because we're just going to be finding the roots of this equation. And you remember, it makes a big difference whether we have the discriminant of this this quadratic equation being 0, positive, or negative, and that will be the case again. So the first case that we're going to talk about is when the discriminant is greater than 0, and that means and corresponds to terminology of saying that the system is what we say is over-damped, because the damping coefficient beta is large when compared to the spring constant K. And so if you were to solve that then, when the discriminant is positive, you'd have two distinct real roots, and so you would get C1 e to the m1t plus C2 e to the m2t, and if we put that as using our notation, we would have the roots are going to be, we're going to have minus lambda, and then it's going to be plus or minus square root of lambda squared minus omega squared. By the way, these t's here are not under the radical, just like they're not under the radical up here. I don't like the way that's typed, but that's the way it appeared on the notes that I was sharing with you. So this equation represents a smooth and non-oscillatory motion. It doesn't oscillate like it did in the previous case when we had it free and undamped at all, and the motion will tend to look something like this. Let's look at an example of this. So we take the spring and mass system from the first example, so many things haven't changed, but this time we'll attach a damper to it, and the damper we know exerts a force of 17 pounds when the velocity is 2 feet per second. So we're going to find this displacement at any time, and we're calling that u of t in this example. So using the data about the force when the velocity is 2, the damping force, we can solve for what beta is, and we will find out that beta ends up being 17 over 2, and when we put it into the equation, this is ma, and so on and so forth. The differential equation we have that. These are the initial conditions from the first problem, but now we have different roots, and the roots are going to be -7 plus or minus the square root of 145 all by 2. But since we're pretending to be engineers, we are plugging that into a calculator, and we're getting these numbers as engineers. And we can use those initial conditions to find out what our coefficients are on the solution, and this time you realize the coefficients are going to be something different because the functions themselves are something different. And so we get an expression that looks like this: minus 0.5198 e to the negative 2.4792t plus another coefficient there, and this is e to the minus 14.5208 times t. And if we were to graph it, we would find a situation like that. So that's what the solution looks like so far. So we've talked about being underdamped or undamped, and we've talked about being overdamped. And now what we're going to look at is we will look at the second case. The first case was totally undamped. This one was, we had damping, but we had it being, let's see, I guess it was overdamped. And now what we're going to do is we're going to look at a thing called critically damped. And critically damped corresponds to the case where the discriminant is equal to 0, which you remember causes us to have a double root at that value. The value is minus lambda. And so what happens here then is we will have the solution is going to be x of t is equal to e to the minus lambda t, and then we have c1 plus c2t, because this was our solution, and that's just writing the solution differently. And so the motion actually is going to be similar to that of an overdamped system, but it does look different, and the solution is different because I have that factor of t there. And let's look at an example of this then. So now what we're going to do is take the spring and mass system from the first example, but this time we're attaching a different damper to it that will exert a force of 12 pounds when the velocity is 2 feet per second. And so we need to find, again, the dampening coefficient. And again, that's proportional in this problem, not necessarily your take-home problem, but in this problem it's proportional to u prime. So we take 12 is equal to beta times u prime. That tells us that beta is equal to 6. We substitute that into the differential equation with everything else being the same. And so we have that, multiply all the way through by 2, and we will have that, and there's our initial conditions again. You know how to solve that. It's good practice for the final exam to be solving that. But what we will get is this is our solution. You can see we have negative coefficients in both cases, and here we have t e to the minus 6t. And so this is called critical damping, and here's what the picture of that will look like if we were to graph that function u. Now the final case that we're going to look at is when we have what is called being underdamped, and this is when what you have is the discriminant, the b squared minus 4ac, is less than 0. And as you know here, we're going to get imaginary roots, and this I, just like the t before, those i's are not under that radical. They really are supposed to be out in front of that radical, or written another way, but this is the way it was typeset here. So what we're going to get in this case then is the roots are going to be have imaginary components. That's going to generate sines and cosines as well as an exponential in front of it. And so the solution for this one is going to be e to the minus lambda t, c1 cosine omega squared minus lambda squared, all under the square root times t, and omega squared minus lambda squared, and again times t. And these t's are not under the square root either. And so what you can see is the motion is oscillatory in this case because of the coefficient of that. The amplitudes of the vibration go to 0 as t goes to infinity. And if you look at this picture, this shows you the difference between an undamped system and an underdamped system. And what you're still going to have is oscillation, but it dies out. Now, as before, and we're going to do this again, but as before, when you have something that looks like this, we can move this to an alternative form, where we have an amplitude, and we change the trigonometric sum of the trigonometric sines and cosines to either a sine or a cosine. But then we will still have e to the minus lambda t there, and these are the equations we used before, and we'll look at an example of this in just a bit. In fact, immediately. So now what we're going to do is take the spring and mass from the first example. Again, I'm just using this over and over again, but I'm changing things that matter. And for this example, let's attach a damper to it that will exert a different force, a force of 5 pounds, when the velocity is 2 feet per second. And then we want to find the displacement at any time t, and we call that u of t. So here we go again. The biggest thing to do is find the coefficient associated with the dampening, which again we're assuming on this that is proportional to the velocity. So we find that beta, the damping factor, is 5 over 2. So we substitute that into our equation. We multiply all the way through by 2 to get this. There's our initial conditions from before. But this time when we solve it, we're going to get two roots. Minus 5 plus or minus, this is I, times the square root of 119 all divided by 2. So that means our solutions then are going to be u of t is equal to e to the minus 5 halves t. It's c1 cosine of that argument plus c2 sine of that argument. And if we put our initial conditions in, we can find out the values of those coordinates, those coefficients rather, of the sine and cosine. And if we want to convert it, and I would encourage you to practice this just a little bit, but what we're going to do is that the amplitude is going to be, we square these values, and the values of the coefficients, and we take the square root, and again we're being engineers, so we're rounding that off, and then we'll have phi, and phi is either the arctangent or it's going to be the arctangent of that value from your calculator plus pi. Now in this case they're both negative, which means we're in the fourth quadrant, so it's going to be let's see, we're in the fourth quadrant, so that is going to be in the fourth quadrant, and what we're doing is we're adding that, so we're subtracting the cosine. So that's the solution to that, and if we were to graph a picture of that, we're going to see that yes, we get exactly what we expect it to do. We do have oscillation happening, but it dies out as time goes on. So that's the behavior that we have, and that's the second video. I will see you in part 3.